Okay, welcome everyone to my continuation of what are my favorite theorems, my very biased collection. Today, not really a theorem, well, there will be a theorem, but more like a strategy. A nice and actually a little bit surprising strategy. Well, surprising is that it actually works pretty well in practice. So the idea of randomness rocks, or more formally speaking, maybe randomized algorithms, which is kind of weird because randomized algorithms are kind of differences, kind of exactly opposite poles. Algorithm, very deterministic, randomized, well, random, kind of the opposite of deterministic. And it still works in practice. And I'm going to use a specific example for which I will write down a theorem in the end. But I give you another example as well, but you can think of many examples along the same line, and randomized algorithms are quite of a big field of computer science nowadays. And here's the idea. So for me, an algorithm is kind of really a deterministic structure. Algorithm is a deterministic procedure, a deterministic structure, a certain input, a certain output, and it always does the same, right? It's kind of algorithmic, it's deterministic. So whatever you do, whatever the computer does is completely determined by basically the structure of the procedure. And so what could be a random algorithm? That's kind of the opposite, as random is kind of the opposite of a deterministic procedure. It's choosing something at random. I'm not going into details what random means mathematically, but you could think of it as really being the opposite of an algorithm, so of a deterministic structure. And a random algorithm is kind of this idea that it really doesn't run always in the same way. It still has an input and an output, and there will be still an algorithm involved, but this algorithm is spiced up with a degree of randomness. Well, not so much, but up to a certain point where it really helps. And I think the way to understand what this really means is to look at an example. And my example for today is the so-called Quicksort. One of the sorting algorithms, pretty simple. I'm going to explain it in a second. Pretty simple algorithm. Depending on your problem, you might want to use different sorting algorithms, but this one is certainly among the most famous. And it's actually pretty simple to describe. So the goal is to just sort a given set. Here, my set X. It's definitely not sorted 9, -3, 5, 2, and so on. And you want to sort it. And the way to do this is to choose a certain pivot, a certain element from the set that you call P, pivot, whatever, and it divides the set into the guys that are smaller and into parts that are bigger. Bigger or equal, strictly speaking, because you could have the repeated entries, but I will just say bigger anyway. So you have the 3 in the middle. That was the pivot that was chosen in the first step, and everything that is smaller and everything that is bigger. And then you divide and conquer. So this was divide and then you conquer in the sense that you just repeat recursively. So you next apply the same algorithm to this set. You choose a pivot, put it in the middle. To this set, you choose a pivot, put it in the middle. Split it into lower and bigger, and continue and continue and continue until you hit, well, one element sets, which by default are sorted, I guess. One element sets are always sorted. And this is now your sorting here of your original set. You just connect all the one element sets in a row. -6, -3, 1, 2, 5, 6, 8, and 9 is the sort of the first given set here. And this is the so-called, as I said, divide and conquer algorithm, because you kind of produce 2 sets and run the algorithm again on 2 smaller sets, and then you produce 4 smaller sets and run the algorithm again on those 4 smaller sets, and so on and so on. And actually pretty fast. But kind of the crucial point here for today is, how do we actually get this pivot? In this situation, or in this example, the pivot was always just the rightmost element of the new set you got. Right? So this was a given set. You take the rightmost element and you get going. You can't take something like the middle element because you want to sort it in order to figure out what the middle element, so the middle in a certain term of size, the middle element is, you don't know, but you can take something like the left element in the input or the right element in the input, something that's not related to size. And choosing such a pivot is kind of crucial depending on what kind of input sets you have. We will discuss that further. And the main idea of randomized quicksort is to basically choose a random pivot. And the reason why you like to do that is, let's say in this very degenerate situation, where, well, so the kind of the best case scenario here in the divide and conquer is if you always kind of start with 1 and you do divide it evenly into 1/2 and 1/2. So roughly two sets of the same size, and then you divide those in two sets of the same size, and you divide those in two sets of the same size. So equally sized sets, that's kind of the best case scenario you can hope for. And with contrast, the worst case scenario is this thing as above here, where, well, you split off 70, but actually it's not really efficient. So you have 4 and 2, 3, and this really breaks down very quickly because you've just chosen your elements in a bad way. In particular, if your set is already sorted and you always pick the biggest one, and then it's very boring. You will always just, well, if you have a certain set here, certain elements, and you always pick the biggest one, you will always divide it into a very long thing and a very short thing. And that's just in every step. So that's really the worst case. So I say it again, the best case scenario is when you divide evenly, and the worst case scenario is this extreme scenario where you have a very long and a very short one. And you really want to avoid that. And depending on your input, if you have a pre-choose the deterministic way to choose a pivot, you might always end up in the worst case scenario, which is really bad. And the idea is then, well, as long as you don't know what's really coming as an input, so you have no idea what the input is, choosing a pivot at random kind of avoids the worst case scenario. So in the end, the expected situation is much better in this randomly chosen setup of a randomly chosen pivot. And this is now an example of a randomized algorithm. So basically the algorithm is deterministic, right? You just split sets into bigger or smaller. Just in every step you have some random element, namely the choice of kind of the pivot element, so the one that splits the two sets into smaller and bigger. And here comes now the comparison. So I take a set X with n elements, okay, fine. And I want to sort it, of course. And the expected and the worst case for the randomized quicksort are those, so n log n or n squared. So the worst case is n squared, and much faster n log n, the expected case scenario. And if you take a plain quicksort, and the plain quicksort would be something like this, where you always choose, let's say, the rightmost element in your sorting case, the average case, respectively, the worst case are n log n or n squared. So worst case stays the same, but there is this mild and in practice very important difference between the expected case and the average case. Right? So what is the difference? Well, average just means it's on a random input, it will run with, in this case, n log n. And expected means with a really high probability on every input, it will run with n log n, which is a much better result, right? Instead of on a random input, it will run in n log n. You're saying with a really large probability, and you can write it down explicitly in this example, the probability, it's very close to 1, with a really large probability on every input, you will run with n log n. Right? So really making the algorithm probabilistic, so giving in a random element, gives you more control over the running time. In almost all cases you will consider, you will almost never, you still have n squared as a worst case, but you will almost never hit it. In contrast to the plain quicksort, where you might be really unlucky and sets that you want to sort are already kind of basically sorted, and then you run into this worst case all the time, basically. That's kind of the idea, right? So making the algorithm more probabilistic gives you more control over the running time. You have the same expected case as for the average case in this case. You don't change, I should say that again, you don't change the worst case. They will always be a worst case, you don't change it, but the difference is you kind of never really hit it. And that's kind of the idea of randomized algorithm. So when you have no control over the input, you don't know whether it's random or whether it's already sorted or whatever, you should really run a randomized algorithm because it's kind of performing best in that situation. So randomness performs best if you have no idea what comes at you, right? So if you have no idea what is thrown at you, acting randomly is usually a good idea. Sounds a little bit strange, but anyway, that's how it is. So acting randomly when you have no idea what comes at you is usually a very good strategy. careful. I'm not saying that it's always optimal strategy. So if you know what comes at you, there might be a really better way of doing it than just acting randomly, which you maybe also know from real life. Of course, acting randomly is very often not the best case scenario you can actually, or the best option you can actually choose. And the point is randomized algorithms kind of always do that, and not just for Quicksort, but way more general. So let me run an example for you, another one. So so-called smallest circle problem. It's pretty cute. I run a Mathematica code linked in the description now. So here's Mathematica, and here's a circle. So the blue thing is a circle and a collection of points. You can vary the number of points. I have 50 points in this example, and you can drag the points around. Let me use a few points. For example, those, you can drag the points around, and the task is to find the smallest circle containing all those points. And of course, if I move my point here within the circle, I already found the smallest circle, but the smallest circle really depends, as you can see, on my point. It gets bigger and bigger and bigger, and really varies depending where I put my point. And this problem goes back to Sylvester. So problem, I said again, find the smallest circle encircling a given set of points, in this case, 13 points. I don't know how you feel about this problem. It doesn't sound to be completely trivial to me. So how to find this smallest circle? Kind of what you need is you need to choose 2 points or a few more points in a very selective way and then draw a circle around them. But what kind of points to choose is not so obvious. And a randomized algorithm here actually does the trick. It goes back to this person here, and therefore the algorithm has the same name, and it works as follows. So we have a set of points, which I call X, and this algorithm calls P, whatever, and a set of boundary points R. Okay, and the algorithm is kind of, again, some of a recursive divide and conquer type algorithm. Not really divide and conquer, but it's certainly recursive, and it works as follows. So you pick a random element from X, respectively from P, and run the algorithm on X minus P, and then you put in the point again, and you just check whether your circle contains a point or not. There's one slight, great idea here, a slight catch if you want. You're keeping track of the boundary, which is denoted by R. So R is a subset of X. So my point could be in X or it could be in R. And depending whether it's strictly in X, then the new circle I found here will also contain P, and I don't care. So this is just my circle for the set X. And if it happens to be in R, you kind of run it again on this set, and then you get this recursion, making R always bigger and making P always smaller. And the recursion runs pretty good. And the point here is that you kind of, again, how to pick P. There's no really preferred choice for P, so you should pick it randomly. And the expected time for this algorithm is really, really fast. So it's actually O of n, which is ridiculously fast compared to, I think this problem looks really, really complicated. But in the end, I mean, runtime n is the number of points. The number of points in the number of points is really, really fast for this problem. So I say it again, you kind of choose randomly a point because there is no preferred choice, and the expected runtime for this algorithm, which is a little bit sophisticated, you need to take care of the boundary, but basically you remove a point and run the algorithm, remove a point and run the algorithm, and so on. The expected runtime for that is O of n. Okay, so this video was basically about Quicksort, if you want, because I like Quicksort. Quicksort is pretty cool idea. It runs very fast. It wasn't all that obvious. It took quite a while. So it's roughly from the 60s, 50s of the last century as an algorithm. And the point about randomizing it is you kind of want to avoid the worst case scenarios with a really high probability, which I haven't written down, but the probability is really, really close to 1. And you almost never run into those, and you are almost always, if you want, in the best case scenario where you get n log n. So the idea of randomizing an algorithm in the end is to put in a slightly random element to avoid that your algorithm, which is deterministic, just eats a certain input, which are kind of always in the worst case, and your algorithm just always runs in the worst case situation, which you can really avoid if you use, well, some kind of randomized input, in this case, a random choice of an element or a random choice of a point, something like this. Anyway, I hope you enjoyed my random video, and I also hope to see you next time.